Hello students, the chapter we're taking today is Thermal Phenomena and it's on page number 330. The first topic out here is thermal expansion. Therm, we know it implies heat or temperature. Expansion means to expand, to increase in size. All substances, when they are heated or when the temperature increases, they expand in size. And the reverse thing happens when they are cooled. That is, when they are cooled, they contract. Contract means to shrink in size. And this happens for all the three states of matter: solid, liquid and gas. But the expansion and the contraction happens at different degree. Out here for the gases, for the same increase in temperature or for the same supply of heat, gases expand more than the liquid and liquid in turn expand more than the solids. Now let's see the thermal expansion in case of solids. We're given out here few examples. The first one, here we have got a glass jar which has got a metallic cap. You can take the example of jam bottle at home which has got metallic cap. If it's too tight and you can't open the jar, what you do is you place the bottle in front of the flame or over the flame so that the metal cap gets heated. And after that you can easily open it. The reason out here is because of thermal expansion. When the metal cap is heated, it increases in size and the cap loosens, so you can easily open the bottle. The next example we're given here is that of railway tracks. I hope everybody has seen railway tracks, and if you have noticed, the railway tracks will have some gaps in between. Small gaps are left in between. This railway track, the rail, it is made up of steel. So they expand when the temperature is high and they contract when the temperature is low. So during the day or during summer when the temperature is high, they expand. And at night when the temperature is low or during the winter season, they contract. For this reason, the small gaps are left in between the rails. If the gaps were not there, then there wouldn't be any place for this rail to expand. So what would happen? They would bend. They would bend like this. So the train running on these tracks may go off track and they get derailed. So to prevent this, small gaps are left in between. The next example is that of a burning kerosene lamp. This kind of lamp, I hope you have seen it. And out here, the chimney, it is made up of glass. Now, if you put some drops of water on the surface of the chimney, or if some drops of water falls on the chimney, okay, I'll draw it out here, falls on the chimney, what would happen is this glass will crack. The reason is the cold drops of water out here contracts the outer side of the glass, whereas the inner side, it's still hot because the lamp is still burning. So there would be uneven expansion out here. The inner surface is still in the expanded form, whereas the outer surface of the glass, because of the cold water, it tries to contract. So because of this uneven expansion, the glass cracks. Next we have got two experiments. The first one is the ball and the ring experiment. Now the simple experiment shows that the solid expand on heating and contract on cooling. And for this experiment, the apparatus required is a metallic ball and a ring. So we have got a stand out here from where the ball, the metallic ball, is suspended with the help of a wire or a string. And we have got a ring out here. The size of the ring is such that this ball can just pass through it, just passes through the ring. The size is neither too big nor too small, but it's just the size of the ball. For the experiment, we are going to heat this metallic ball and we'll try to pass it through the ring. We observe that the ball after heating won't pass through the ring. We'll let it cool for some time, and after cooling, again this ball can pass through the ring. This shows that this metallic ball, on heating, it expanded in size. That is why it could not pass through the ring. On cooling, it shrunk back to its original size, and now it can pass through the ring. So this experiment proves that solid expands on heating and contracts on cooling. The next experiment we have is that of bimetallic strip. Bi means two. So we have got a metallic strip consisting of two metals, A and B. This experiment shows that different solids, they expand by different amounts, meaning some expand to a greater amount and some expand to a lesser amount. Now for this, we are going to heat the bimetallic strip, and after heating it, it is observed that the bimetallic strip bends like this. Now, if these two metals were separate, were not joined together, and after heating, it can be seen that the metal A, which expands more, will be longer than the metal B. But since they are joined together on one side, these two metals A and B cannot expand independently. So the strip bends. And out here, the metal which expands more will be on the outer side. Next, we are going to see the coefficients of thermal expansion of solids. For this one, I want you to make notes in your classwork copy. You copy down the name of the chapter and the subheading, coefficient of thermal expansion. Now in the previous two experiments, we learned that solid expands on heating and contract on cooling, and that the solid expand by different amount. Now to measure and compare the amount of expansion of different solid, we have got a term which is called your coefficient of thermal expansion. We know that a solid, when it expands, it grows in length. It expands in length, the length increases. There is expansion in the surface area, meaning the surface area increases, and also there is increment or the increase in the volume. So that is why we have got three coefficients. The first one is called coefficient of linear expansion, meaning length. Next one is coefficient of surface expansion. It's for the increase in surface area. And the third one is coefficient of volume expansion for the increase in the volume. So now let's just see the first coefficient we have is coefficient of linear expansion of solids. The coefficient of linear expansion, it is represented by the letter alpha. Now let's see the definition, what exactly it is. The coefficient of linear expansion of a solid is the increase in its length per unit length per degree rise in temperature. Now let's take a metal rod. Suppose the length of the metal rod is, let's take it L1, and the temperature is T1. Now we're going to heat this metal rod. Now when the metal rod is heated, it increases in length. It expands. It increases in length. So now the new length, let it be L2. This new length, let it be L2. And now temperature has increased to T2. Now here, increase in length. The increment of length, this portion would be L2 minus L1. Next, increase in length per unit length can be written as increase in length is L2 minus L1 divided by your L1. L1 is the original length. So increase in length per unit length would be increment in length divided by the original length. Then rise in temperature is T2 minus T1. T2 minus T1. So by definition, the coefficient of linear expansion alpha would be L2 minus L1 divided by L1 divided by T2 minus T1. Coefficient of linear expansion of a solid is increase in its length. This is increase in its length per unit length divided by the original length per degree rise in temperature divided by the increment in temperature. So this is alpha. Now let's see the unit of alpha. Unit of alpha. Alpha is L2 minus L1. This is length, and in denominator also there is length and there is temperature out here. Now the unit of length, it can be in centimeter, it can be in meter. Now the length is in the numerator and the denominator as well, so it can be cancelled. So now we are just left with the unit of temperature, which can be written in Celsius degree or the Kelvin scale, either in the Celsius scale or in the Kelvin. So the degree Celsius in the denominator, when you take it to the numerator, it becomes degree Celsius inverse, or to the power minus 1. So the unit we got is per degree Celsius, or in the Kelvin scale it would be per degree Kelvin. Now here the unit of alpha it does not depend upon the unit of length, because see, the unit of length gets cancelled. It's the ratio of the lengths. So it does not depend on the unit of length, but it depends on the unit of temperature. Next we have is the coefficient of surface expansion. Expansion in the surface area. The area of the solid. Surface area of the solid. It is denoted by the letter beta. Let's see the definition. It's similar to that of alpha. The coefficient of surface expansion of a solid is increase in surface area per unit area per degree rise in temperature. Now let's take a solid. Let's take the surface area of the solid to be S1, and let's take the temperature T1. Now let's heat that solid. When it is heated, it expands, so the surface area increases. So the new surface area, let's take S2, and the temperature, let's take it as T2. Now increase of surface area would be S2 minus S1. Increase in surface area per unit area would be increase in surface area S2 minus S1 divided by the original surface area, that is S1. And increase in temperature is T2 minus T1. Now, by definition, B, that is a coefficient of surface expansion, beta becomes S2 minus S1 divided by S1 into T2 minus T1. Increase in surface area, S2 minus S1, per unit area, that is your original surface area S1, per degree rise in temperature, T2 minus T1. Then the unit of beta out here also, the unit of area gets cancelled, so we are just left with the unit of temperature. So unit of beta becomes per degree Celsius, or in Kelvin scale per degree Kelvin, similar to your alpha. Now beta also here, it does not depend, or the unit does not depend on the unit of area, because it's the ratio of two surface areas, but it depends on the unit of temperature. Now finally we have got the third one, coefficient of volume expansion. It is denoted by the letter gamma. And coefficient of volume expansion means the increase in the volume. Increase in the volume of the solid. And this one, I want you to refer book, understand it, try to understand it, and write it down by yourself. It's similar to your alpha and your beta. I'll just read out the definition. Let's see. Coefficient of volume expansion is the increase in its volume per unit volume per degree rise in temperature. You are taking out here V1 and V2 at temperature T1, T2, and by definition it turns out to be V2 minus V1, V1 divided by V1, T2 minus T1. I hope you can understand this. Okay, write it down in your copy. Next, we have got the relation between the three coefficients alpha, beta and gamma. Please put a tick mark out here in the book and write it down in your copy as well. So let's see, alpha, the relation would be alpha is equals to beta divided by 2 equals to gamma divided by your 3. This is the relation. Kindly write down what the terms imply. Alpha is the coefficient of linear expansion, beta coefficient surface expansion, gamma coefficient of volume expansion. I want you to memorize this one. Now, after that, we have got in the book, we are given a table, and here we are given the coefficient of linear expansion, the values for different substances. I want you to go through this one, and let's just see. Here, if you compare, you can, with this table, you can easily compare which one would expand more and which one would expand less for the same increase in temperature. Let's take the example steel and aluminium. Steel, the linear expansion is 11 and aluminium it is 23. So we can say aluminium expands more than steel for the same increase in temperature.